Okay, next topic, couples. We're going to talk about couples, but not the kind of couples you're thinking about. Two forces, F and minus F, uh, if they have the same magnitude, are parallel, and opposite sense are said to form a couple, right? So these things, they have the same magnitude, they're parallel to each other, but they have the opposite sense. It forms a couple. So what is a couple going to do? A couple, does it have any tendency to rotate or to translate? No, right? For every bit of force going in this direction, there's an equal and opposite amount going in this direction. So a couple has no tendency. It doesn't cause any translation. It does, however, cause this thing to spin, right? It causes a tendency to rotate, and that tendency to rotate is captured by the moment of the couple, right? So we have the moment is r cross f, always r cross f. So here we have this axis, right? So the moment about this point right here is this r cross this f plus this r cross this f. The beauty is, so r cross f plus r cross minus f, right? Because of the minus direction. Well, you can go through and you can pull out the r's because it is distributive, and you can figure out that it is the RA minus RB cross F, which is just this R cross F. And the magnitude is RF sine theta. So RF sine theta, or force times distance. And that is the takeaway. The magnitude of the moment of a couple is the force times the perpendicular distance between these two forces. Now, this is kind of an important part of this, is the moment vector of the couple is independent of the choice of coordinate axes, right? Does that make sense? Because we actually picked this point here, and you go through and you figure out that it's the same as if you pick the point here, right? And so we're saying it doesn't matter whether you take the point here or here, this is independent of the coordinate axis. So what that means is this is a free vector. Okay, we talked about this briefly earlier in previous chapters. A free vector means that you can put this vector anywhere that you want and it will not change the analysis. Now, it's a free vector. You have to have the right direction, you have to have the right sense, but where you apply it does not affect it. So again, let's talk about the moments of the couple. Two couples will have equal moments if the following conditions occur. If the force times the distance is the same, right? So if you double the force, you can half the distance. Your moment's going to be the same. And the two couples lie in parallel planes, very important. And the two couples have the same sense or the same tendency to cause rotation in the same direction. Okay. We have our lug wrench, right? Here's a classic lug wrench. You got this, you pull in this direction, pull in this direction. You are providing a couple. Right? This lug wrench is not trying to move this way, it's not trying to move this way or up or down. It's, as far as this bolt is concerned, it is just getting twisted. Nothing else is happening, it's getting twisted. So you have to apply a certain amount of force to this. Well, what happens if you reach out further? You get a bigger lug wrench and you can hold on to it way out here and way down here. Well, in order for this bolt to feel the same effect, you don't have to push as hard. So again, if you make this twice as big, you can push half as hard. Now this is one of those things that everyone's done, right? When you're trying to move something, it's always easier to get some leverage on it to get further away from what it is that you're rotating it about. That's what you're talking about, is we're talking about this couple. So a lug wrench is a perfect example of a couple that it's not trying to translate, you're not trying to move the bolt anywhere, you are just simply trying to rotate the bolt. Okay, let's talk about the addition of couples. If you have let's talk about two intersecting planes. So you have P1, right? This is this plane, and it has a couple, F1 and minus F1. So there's a couple in this plane right here. And then we also have this P2 plane, and it also has a couple, F2 and minus F2, so this couple is in this direction, right? So moment of 1 is R cross F in plane 1, moment of 2 is R cross F in plane 2. Okay, so the resultants of the vectors also form a couple. Okay, so R cross R, right? So this, if you add up this F1 and this F, you have a vector R. So if, say, let's take the moment about point B. It's R cross F, right? In this case, that force is the resultant vector, we're calling it r. So r cross r. Well, what is r? R is F1 plus F2, right? And where you go through, and if you can distribute that out, r cross F1 plus r cross F2. But hey, hang on a second. We already saw that. R cross F1 is what? It is the moment of 1, and r cross F2 is the moment of 2. So therefore, the moment is m1 plus m2. So what does that mean? This means that the sum of two couples is also a couple that is equal to the sum of the two couples. So it's just really nice. If you know that you have two couples, you can just add up the vector portion of those couples, and then that is your final answer. Now, we want to represent couples with vectors, right? So you have a couple here. A couple can be represented by a vector with magnitude and direction equal to the moment of the couple. So what does that mean? You have this couple, right? This is going to try to rotate about in its plane. So the vector is perpendicular because it's r cross f, right? It's going to be perpendicular to this plane, and the magnitude is the force times the distance. Okay, but what do we say about this? We said that that is a free vector. And since it's a free vector, you can apply it anywhere you want. So yeah, you can apply it here, but hey, let's make life easy. Let's apply it at the origin. Okay? But couples obey the laws, well not but couples obey couple vectors obey the laws of addition of vectors, which is not overly surprising. They are free vectors, which we just talked about, so we can put them anywhere we want. And then the nice thing is that they can be resolved into component vectors, right? So this couple here, this vector can be said to say that there's a y component of it, there's an x component of it, and there's a z component of it. And again, just like we talked about a little bit ago, the x component of that couple is the portion that's trying to rotate about the x-axis. The y component is the portion that's trying to rotate about the y-axis, and the z component is trying to rotate about the z-axis. So why do we care? Why in the world are we doing this? Well, it all comes down to this. We want to resolve a force, a single force, into a force and a couple. So here we go. We have our potato, okay? And if we have this force applied here, F, we can't just arbitrarily move it to some other location without changing the effect on the body. So imagine if you apply this force F, and this is in outer space, right? This potato is going to start moving in this direction, but it's also going to start rotating about in this direction. Okay, so, but we really want to do our analysis based on this force being applied here. Well, if we just arbitrarily move this here, are we going to move in the same direction? Absolutely, right? We're still going to move in this direction, but now we're probably going to start rotating around in this direction, which is definitely not the same thing, right? So we can't just arbitrarily move it without modifying its action on the body. So what are we going to do? We're going to say, hey, you know what? Let's, here at this point, let's attach a force and an equal and opposite force. Okay, so again, it's like add one, subtract one. It has no effect on the body, so nothing's changed. But now you can look at this and say, hey, wait a second, I recognize that. This force and this force add up to be what? This is a couple, right? And with a certain magnitude of a moment, and that moment is the force times the distance, right? And so I can put, hey, instead of this couple, I'm going to replace this couple with my vector of the couple, and I have left over this force F here. So the three forces can be replaced by an equivalent force vector and a couple vector. And so we've gone from having a force here to saying that there is a force in the same direction, so that force has to stay in the same direction, because translation is actually pretty straightforward, right? Whether the force is here or here or here, it's going to try to make it move in one direction, but the rotation is what changes. So we're going to add in basically what we're doing. So what we change something by moving this to here, from here to here, we change this tendency to rotate. Well, we fix that by adding in the couple. And we're going to do the same thing about some other arbitrary point O. You can go through and you say, hey, I'm going to move this to some arbitrary point O. The moment is R cross F. We can go through and figure out the same thing. Basically, it's just the same thing, that you can move it to anywhere you want as long as you make the appropriate changes to the moment vector or to the couple to account for that. So what is this saying? It's basically saying that you can apply a force anywhere you want, but when you move it, you need to account for what changed in its tendency to rotate, right? If you keep the force in the same direction, its tendency to translate is going to stay the same, no matter where you apply that force. But definitely, you can see scenarios where it's going to change its desire, its tendency to rotate. So if I move it somewhere where it has much less tendency to rotate, I need to add that back in. So I'm going to add that in through this couple. Let's do an example of this right now. This is example 3.6. This is a good example of this.